Okay, hello everyone, good morning. My name is Pau Agost Barreda. I come from Universitat Politècnica of Valencia, where I study industrial engineering. Today I am going to present my bachelor thesis, which consists of the construction of a Stewart-Gough platform. Here we can see the table of contents. First I will start with a short introduction. Then we will discuss about the different parts of the platform, and later we will talk about the joystick. And finally, we will end the presentation with a short demo of how the joystick and the Stewart platform works. First of all, I want to do a brief introduction. The Stewart-Gough platform is a robotic system that has 6 degrees of freedom, 3 rotational and 3 translational. There are 2 types of platforms, the rotary actuators and the linear actuators. The linear actuators has 6 independent legs that each one can vary in length, so you can achieve the position that we want. While the rotary action has servos that change the angles to move the rods and achieve the position that we desire. In this project, we are going to use the rotary actuators because they are cheaper, so everybody can do a Stewart platform. It has lots of advantages, such as high load capacity and also high rigidity and stability. It has a fixed base and also a movable platform connected with 6 legs, as you can see. And it is used in so many fields, such as, for example, in flight simulators, because the platform mimics the movement of an aircraft, so it is used to train the pilots. Also, it is used in medicine and robotics, for example, for surgery, because it has very good precise movement. And also here we can see a GIF of a brain operation, and we can see how it works and how it moves. First of all, I started with the construction of the base prototype. As you can see here, with the laser cut, I cut all the pieces of wood and assembled it using wood glue. This is the sketch from SolidWorks. And also, I did a test hole because the rods are of 4mm diameter, so I used 3.8mm to be sure of we are having a smooth fit. Once the base was done, I put the servos in the correct order and also added some adhesive tape to increase the stability. The servos control the angular position, the speed and the acceleration, and they are used in many fields. And you give the servo, you want the servo to move to a certain position, so you give him a pulse, and this pulse determines the desired position. Then the circuit of the servo controls the current position with the desired position, and so finally then with the necessary torque and speed, it goes to the desired position. Also here, in this image, we can see that shorter pulse means small angles, while bigger pulse means larger angles. Also I want to mention that if you give to the servo a very big pulse, you can break it because you are moving the servo into position beyond the range. Then I started designing the servo arm attachment, as you can see here in SolidWorks design. And I should be clear about the length of the piece because it should be less than the higher of the servo, because if not it will hit the base and create a collision. And also I did some different tests, as you can see there, then you can see the pieces. I did 3 types of the different widths of 10, 15 and 20mm. And we finally chose 20mm because it was the one that interfered least with the rods, so the rods can move freely without hitting the servo attachment. Also it has a hole in the middle to put the screw of the servo and be attached to it. Okay. In this slide, we can see how I put the M3 inserts. In this picture, you can see clearly. I use a head insert machine. I'm using this method because I use some wood because the wood is avoiding the need for high temperature. So since it is as an insulator, so we didn't need to heat the tool. So with low temperature, we were able to put the M3 insert straight. These are 2 versions of the superior attachment that attach the rods with the superior platform, as you can see there. And we are going to use the first version, but also the second one has 4 chamfers in the corner to avoid the rods hitting the superior attachment, but with this one it's okay, so I didn't put the second version. And here I also want to mention some printing problems that we have. because when you are printing something, it has some tolerance. So if you want to do a diameter of 3.8, you should design it previously in SolidWorks at 3.9 millimeters, and then it will be smaller. And the M3 insert are 4 millimeters, so it's good enough, and it's a snap fit. Those are the prototype rods. As you can see, they are formed of a wooden stick, and using the glue gun, I attach them with the ball joint, and they are flexible. And in the prototype we use this type of mechanism because it's better to break the wood rather than the servos, because in the beginning the servos move to position that we don't want. So that's why we use some wood. This one is the mechanism that will attach the rods to the upper and lower attachment. It's the M3 insert, the screw, 2 nuts, and the metal sphere that allows the rotation. Also, I did some tests about the length of the rods, and we agreed of doing 110 millimeters because it doesn't interfere with the lowest position of the platform and it doesn't hit the base. Thanks to inverse kinematics that Albert, the other Erasmus student, is going to talk later, we decided that the superior platform should be bigger than the base because there will be less movement and it will be more precise. And also, it is the opposite way as the base, as you can see in the image. And I did different tests of the sizes and finally agreed of doing 130 millimeters at the large side of the platform. I put multiple holes in the platform, as you can see, for the attachment of the laser mount, and some big holes for the cables of the laser. Now I want to talk a little bit about the laser. We are going to use a violet laser because we are going to use phosphor, and phosphor only gets excited with frequencies higher than green, such as blue or violet. And when the laser hits the phosphor, it emits a photon that lights up, so we are allowed to write and draw there. We have two types of laser, the 1 milliwatt laser and the 200 milliwatt laser. We are not going to use the 200 milliwatt laser because it's too powerful and can damage the eyesight, so we are only going to use the 1 milliwatt laser. I designed the attachment, and instead of printing it in the Prusa printers that use PLA, we are going to use the Mark IV printer because it uses onyx, and the onyx is more heat conductor than the PLA. Once all was done, I assembled all the platform, as you can see here, and also added some cables. And first, we put the superior attachments in the larger side, but then we realized that it will be better to put in the shorter because it creates a triangle, so it gives more stability and more strength. Then Jürgen put all the software, and also here in this image we can see how I use Loctite to attach the servo keys to the servo arms. Once all was done, we wanted to improve the platform, and give more strength and reduce the play. So that's why I started designing it in 3D printed parts. That's the platform. I use lots of holes to minimize the waste of material. And also I put some ribs, as you can see there in the platform, that increment the strength. The mechanism consists of a box. The servo is put vertically, and then we add 2 tabs, one above and one below. The one above has this shape because the cables of the servo had to go out. So once you have put the 2 tapes, we added a cover and screw it we put a screw so it's all tight and the servo doesn't move. I did the same with the rods. I did the design in SolidWorks, as you can see here, and it gives more strength and stability. And also we wanted to minimize the use of support. So that's why I put the rods at 45 degrees and use lots of fillets. Once the parts were printed, I used a screw to attach this part to this. So this is the 3D rod. So I revealed the new platform, as you can see here, and we realized that we have improved the strength and we have reduced the play, so we have achieved our goal. And also here we can see how it's attached the 3D part rods with the upper and lower attachment. Now I'm going to discuss about the joystick prototype. Once it was coated with the laser, I glued them and assembled them. And instead of using servos, here we are going to use potentiometers that they were previously cutted because only move the attachment part. And also we wanted that the middle point of the potentiometer was the same as the horizontal position of the attachment. So that's why we use this tool and this mark to align them, and when they were aligned, we do a little mark on the zero. Once the base was done of the joystick, I did the superior platform using the same rods and the same attachment as the Stewart-Gough platform, as you can see there. Also, I looked for a file on the internet of a joystick, but I adapted to our case, changing the size and also putting a hole through so we can put the cables. And also I designed a button mount to put the buttons. When it was printed, I used M4 inserts to attach the joystick to the superior platform. I also want to mention there that we have some hardware limits because the servo only go from minus 60 degrees to 60 degrees. So to avoid getting to position that we don't want, that's why I put the hardware limits. Also the potentiometers in the range, they are not reliable, so we have to work in a range. And finally, I would like to mention that we use some Teflon, some discs of Teflon that I cut in the laser and put it between the wooden parts because the Teflon eliminates the friction so it can move smooth in the joystick. So that's all. Thanks for listening. Now we will do a short demo of how the joystick and the Stewart platform work, and I hope you enjoy, and then you will ask me some questions. If you want to come close to see or whatever you want, you can.
Yeah, I think. Can you try?
Yes, I think it works.
Are you all activated? Can you check if they are all activated?
No, not all.
Yeah. No.
Yes, now.
Yeah.
Okay. Here we can see the 6 degrees of freedom, up and down, here, and then the rotation. So it goes smoothly and we show how it moves. And also here we can do a game for the kids, for getting interested on the parent, for example, following a maze, and you can do the movement, and the ball will follow the pattern. It's not easy. If you want, you can try. So that's how it works. It's quite precise, the movement. That will be. You want to try or something? Yes. Okay.
Thank you very
Yes.
much, Pau, for the interesting presentation of your work. Now it's time for questions.
Yes.
So I'm looking to the judges if there is any question on this topic.
I had two, but
Yes.
you already replied one. In the beginning, when I saw the white plastic part, I was thinking, okay, how can you reduce the weight? Because that's quite a heavy weight.
Of this?
No, that was one of the first pieces I saw. Is that one in white.
That one, okay.
So I was thinking, okay, how can you reduce the weight?
The weight here.
But I see
Yes,
during the presentation,
yes, I mentioned it, yes.
you already kept in mind that you need to reduce the weight.
Yes,
So,
yes.
And then the second one, if you want to use it for different applications,
Yes,
for example, in medical, how easy can you change materials?
To improve the materials.
But for example, if you use something like this in weather conditions, sometimes the material has to be different than you use it for medical.
That's true, that's true. Well, this is just a demo, but the Stewart platform we can change. We can also use metal or other materials and to improve it. And as you can see in the GIF that I said, they have built a huge Stewart platform. And some of them in the GIF it was in the sea, so the weather was really bad. So it worked, but yes, for the demo we use PLA, that is cheap plastic. So, but if you want to improve it, it will be more expensive, but you can also do it with other material, yes.
What is the weakest spot on this application?
The weakest part?
The spot. What will break fastest?
It will break this part. We didn't attach these parts. You can see you can remove that one, because if the servo goes to a position that we don't want, it's better to break to this goes up, it pops up, one of them, so it doesn't break the whole platform and we don't need to rebuild it.
What's the reason of the laser you used?
The laser, Albert is gonna talk about later. His project is programming the software of it. But as you can see, you are able to write or draw something here in the phosphor. And there are also other applications. We should also use the powerful laser that I showed you. And for example, to shoot the bubbles or something. And so there are lots of applications we can do.
Do you have an idea of the maximum load you can put on the platform?
Of the what?
The maximum load.
What's
load? The weight.
The weight. Yes. As it is it's plastic, but you can put. I don't know. We haven't checked how many the weight we can put, but it shouldn't be too much because this can crash. They have good strength, but you can put too much weight because it will put the weight and the servo didn't move as well as we want.
How would you determine it? How doing a test or?
Yes, we can do a test. Yes, why not? We can try to put some weight and see when the servos starting to don't work well. So yes, maybe why not? We can try it. Yes.
Let me give you a tip, because I know where the question is going to go. Each servo has a maximum capacity. It's a turning moment of 7 kilograms centimeter.
7 kilograms, okay.
7 kilograms centimeter. Can you deduce that more or less what the maximum loads can be before the servos start to?
There are 6 servos, so the high should in its servo. So if it's 7, we shouldn't put more than this in its servo. The capacity.
That's not quite correct. So it's a moment. Is that the correct name in English? Torque.
Torque, yes.
The torque is 7 kilograms centimeters.
The torque. Okay.
Yeah.
Okay.
So
we should multiply by the length of the rods.
Which one?
The torque is the so if it's 7, the torque that you put shouldn't move more than 7 per the length of the rods. That's what I think. No?
Not that rod. It's the other. It's the servos. You're not talking about the platform itself.
This one, yes.
Yeah. So
sorry.
Just a guess. You know it's 50 millimeters. It's 5 centimeters.
Yes,
so how
45 millimeters.
How would you deduce the load, maximum load?
The 7 kilograms per meter per 45 millimeters. So that's the maximum weight that we can put.
Yeah. So how much weight?
7 per 45.
7?
7? Did you say 7?
Yeah.
Per 45, 0.045. That's 2 meters.
Yes, but then you also have 6 servos.
Yes, no, and this for each servo, and then you have to multiply for the 6 servos to be the whole capacity.
I also have a question. You talked about this part.
Yes.
Can you maybe explain? So you have these rods here.
Yes.
How do you come to this design? How have you determined the boundary condition and let's say the strength condition? Which are the boundary conditions for this?
Yes, I think triangles give very good strength to the pieces. So that's what I try to use this design. Also, it's a triangular in this shape, and also here has some triangles.
But did you do a calculation or something to determine whether your design is
I see some sketches about how to increase the length, the shape of this, and I saw this shape, and it said that it has very good qualities. So that's why I use, and also orienting 45 degrees. It creates that you don't need support in the printing, so it increases the properties and it's easy to remove. So it gives.
So if I understand well, you did not use any analytical solutions to help you solve this problem.
Well, not an analytical solution, because I know that always forming a triangle gives more strength. That's why.
Okay, but if a triangle would be the solution, then everywhere would be triangles.
Yes, I know what you mean. But you can also see on the electrical towers that when you are applying a force this way, they are all using the triangular method, and it is really strength, as you can see.
Okay. And then you also said that the movement is very precise. How do you determine what is precise?
Well, yes, we are using chip servos and that, but when we started, it didn't move at the same as it was. But we can see that if you move, it follows more or less, and there isn't any play.
You have an idea on the precision in terms of tolerances or units?
No, we haven't checked the units, but that's why we also put the hardware limit. Because when these weren't there, if you go to a position that the servo doesn't go, it doesn't follow, so there is a lot of tolerance, and this is not good.
It's going to become very clear when we use the laser, then we have an immediate...
Yes, in the laser you can see that if it is allowed to write, you can see that it's very precise. In the joystick you can see it very clearly.
But what I want to know, if you have the sending servo, okay, you have the sending servo.
Yes.
It turns, let's say, 45 degrees.
Mm-hmm.
What is the receiving servo doing at that time? Does it make a turning moment also of 45 degrees?
Yes, it goes.
The same.
Well, I haven't done the software, the one is done for Jürgen.
Yeah, but it's not really a matter of software always, it's a combination, it's also mechanical.
No, yes, the servos are good enough. If you send a signal, it changes to the position that you want, yes. Yes.
Any more questions? Okay, then we will finish. Thank you very much.
Thank you so much.